Hello, my good people. Welcome again to my YouTube channel or David Structure Hub. This is a place where you learn, build, and innovate. Today, I want to solve problem number 3 under timber design to BS 5268. And the question is on the board. So the question reads, a cantilever beam of solid section overhung with a clear span of 2 meters on a bearing of 400 millimeter at the support. It is to carry a UDL of 10 kilonewton per meter together with a point load of 8 kilonewton at the end. Design the beam for bending and check for shear and deflection using the following information. Permissible stress is equal to 4 Newton per millimeter square. Permissible bending stress is equal to 8 kilonewton per meter square. Permissible deflection is equal to span over 250. Depth to breadth ratio is equal to 3. E mean is equal to 9.9 kilonewton per meter square. So let's see how you can handle such a question. Solution. The first thing to do is to draw a sketch of this beam. So we have been told that a beam, it has a clear span of 2 meters on a bearing of 400 millimeter at the support. So let's draw the beam and load the beam. So that is our beam, and this is the support. That is the support. So a beam is loaded with a UDL of 10 kilonewton per meter. So we have a UDL at the beam of 10 kilonewton per meter. And then we have a point load of 8 kilonewton at the end. So here at the end, we have 8 kilonewton. Again, a beam has a clear span of 2 meters. So this distance this is a clear span, 2 meters, and a bearing of 400 millimeter. So this is the distance of bearing. We have 400 millimeter, so we convert it to meters. You divide by 1,000, so it will be 0.4 meters, like that. So after doing this, we'll start calculating the maximum moment on this beam. But before we start calculating the maximum moment for this beam, let's determine the effective length. So the effective length remember for a cantilever, we said that the effective length is the clear span distance from here to here plus a half of the bearing. A half of the bearing. So the bearing is 0.4. So we will have effective span of cantilever beam is equal to a half bearing plus clear span. So is equal to a half. Bearing is 0.4 times 0.4 plus the clear span, which is 2 meters. So the final answer will be 2 here, 1, 0.2. So the answer is 2.2 meters. So this is the effective length. And then after getting the effective length, we will now calculate the maximum moment on the beam. So maximum is equal to W L square. Yes, WL square over 2 plus WL. So WL square over 2 is for a UDL. We convert this UDL to a point load by multiplying its length. And then to get the moment, we again multiply by the length, you divide by 2, WL square over 2. Then you come to this point load, which is 8 kilonewton, WL, W times L. So this one will be 10 times L, which is the effective length, 2.2 square over 2 plus W, which is a point load, 8 times L, which is effective length, 2.2. So the answer is 41.8. 41 kilonewton meter. So that is the maximum moment. The second thing to calculate is the shear force. Shear force or reaction, which is V. So V is equal to, V for the UDL will be W L plus W. So this one is equal to 10 times L, which is the effective length, 2.2 plus W, which is a point load. This is 8 kilonewton. So the answer will be so the answer is 30 kilonewton. After there, we'll proceed to design consideration. We'll start with bending. So let's see how we're gonna do this. This question, you have been given permissible stresses, i.e. shear, bending, shear and bending. So there is no need to go and obtain the grade stresses in the table. So we go direct to design consideration and we start with bending. So bending, design consideration number 1, bending. So bending, the formula for bending, we have F is equal to M over Z. So we make Z the subject of the formula, whereby Z is equals to M over F. And since we have our M and we have our F, we will go direct and insert those values in the formula and get the value for Z. So this one will be, therefore, Z is equal to M. M is our applied moment or our maximum moment, which is 41 41.8 kilonewton meter. So we will change kilonewton meter to Newton meter by multiplying 10 raised power 6 over F. Our F is permissible bending stress, which is 8, like that. So our Z will be our Z is 52.25 times 10 raised power 3 millimeter cubed, like that. So the next thing to do is to consider now the ratio, the depth to breadth ratio, so that you can obtain either depth or breadth. So let's see. So depth, we have been told depth to breadth ratio is equal to 3, like that. So you can either make D the subject of the formula or B the subject of the formula. So let's make D the subject of the formula. So D, which imply D is equal to 3B. You cross multiply. Yeah, you cross multiply like that. Again, we know that section modulus, which is Z, is equal to BD square over 6. So we will substitute the value of D by 3B. So therefore, for which imply Z is equal to B, this D we substitute by 3B into bracket 3B raised to power 2 over 6. So Z is equal to, if we open the bracket, 3 square will be 9. B square will be B square. So B square times B will be B cubed. So we have 9B cubed over 6. So we have this dead and we have this dead. So we can equate this value to this dead by saying that 9B cubed over 6 is equal to this value 5225 times 10 raised power 3. So we can calculate the value of B by, you cross multiply 6, you cross multiply, so we will have 9B cubed is equal to 5, 22, 5 times 10 cubed times 6. Since we want B, we will divide both sides by 9 by 9. So 9, 1, 9, 1. So we have remained with B cubed is equal to 5, 22, 5 times 10 cubed times 6 over 9. So we want B alone. So we will get the cube root of B like that. So this cube root will cancel with this. So we will remain with B, so which imply B is equal to 151, 151.59 millimeter. So you can punch this one in your calculator and you will get the answer. So that is how you do it on a calculator. The answer is 151.59 to 2 decimal places millimeter. Then let me wrap this space. Say, then we say B is equal to 175 millimeter because we always take a section in a multiple of 25 millimeter, 25 millimeter. So if our B was 151.59, it means we will go for a value which is higher than this and is in a multiple of 25 millimeter. So this value is 175 millimeter. Then D. So D is equal to, remember, our ratio, we obtain D as 3B from the ratio. So D is equal to 3B. Therefore, which imply D is equal to 3 times B, which is 175 millimeter, which is equal to 525 millimeter. So our section is 175 times 525 millimeter. So this is bending. Let's check for shear. So the shear stress is equal to 1.5 V over BD, whereby V is our reaction or the shear force we calculated earlier, and then the B is this 175 and the D is 525. So the shear stress is equal to 1.5. V is 30 kilonewton. So you convert it to Newton times 10 raised to power 3 over B 175 times D 525. So the final answer is 0.49 Newton per millimeter square. So we compare this with permissible shear stress. So it means 0.49 Newton per millimeter square is less 4 Newton per millimeter square. So section, okay, in shear, like that. Then we will come to permissible deflection. So deflection, let me create space for deflection. Deflection. So under deflection, we have the permissible deflection. Permissible deflection, we have been told, is equal to span over 250. So span over 250. So this one will be span is the effective length, which was 2.2 meters times 1,000 over 250. So this one is equal to, the answer is 8.8 millimeter. So 8.8 millimeter. That is permissible deflection. So we proceed to induce the deflection. Under induced deflection, this is our beam. Remember, our beam is loaded with both a UDL and a point load, as you can see on the board. So the effective span is 2.2. So we will have induced deflection for a point load. The formula for induced deflection for a point load is this one. And then for a UDL, so UDL is 10 kilonewton per meter. So the formula is this one. So we will have this plus this. Then we will have our final or total deflection for the two loadings, a point load and a UDL. So let me create space here. So for a section properties, we have area. So this one will calculate the area for the section. So the area is length times width, which is 175 times 525. So this one is equal to, let's punch our calculator, 175 times 525. 91. So the answer is 91.875 times 10 raised to power 3 millimeter square. And then we go for I. I is B D cubed over 12. So this one is 175 times 525 cubed over 12. So the answer is the answer is 2110.25 times 10 raised to power 6 millimeter raised to power 4. And then we have our first W as 8 kilonewton. Again, our second W as 10 kilonewton per meter. Again, we have our E as 9.9 kilonewton per meter square. So we'll convert this 9.9 kilonewton per meter square to Newton per millimeter square. So you'll multiply by 1,000. So you'll have 9,900 Newton per millimeter square. Again, for this 8 kilonewton and 10 kilonewton per meter, you'll convert them to Newton and Newton per millimeter square respectively. So this one will be 8,000 Newton, and this one will just change the unit. So we'll have 10 Newton per millimeter, like that. And then we can insert these values into our formula and get our induced deflection. If we can insert these values into our formula, this is what we will have. And then by punching your calculator, we will have 1.35 plus 1.40, which is equal to 2.75. So this is the total induced deflection. So we will compare the total induced deflection to permissible deflection. So as you can see, this total induced deflection is less than permissible deflection, which is 8.8. So the section is okay in deflection, and our question ends there.